Hello, in this video, I will talk about how to fit an ordinal regression model using a R function called the polr, P-O-L-R. Okay. First, let's load in a bunch of libraries, mass, dplyr, and library ordinal. Okay. Set a random seed, sample size of 500. So let's generate uh, two continuous predictors with the covariance matrix, and then generate the data using the multivariate normal distribution and assign variable names. And we create another categorical predictor, Z, with ABC categories. And then, okay, now we are going to create the ordinal response, okay? And to create that ordinal response, we have a conceptual model. We think there's a latent continuous variable, and there's several thresholds. And the ordinal response variable will take each response value when the latent continuous variable exceeds certain thresholds. So that is the ordinal regression model's assumption about the data generating process. Okay, so let's say latent variable is it's a combination of all these three variable values, and then there's a cut points, and then now we cut this latent variable at different cut points, and then we generate the dependent variable y and put everything together, and this is what is the data set look like. Okay, and this is the data structure for fitting an ordinal regression model. You get a dependent variable, which is the ordinal, and you can have continuous variables such as x1, x2, and you have categorical variable such as z. Okay, and you can take a look at the summary of the data look like that. Okay, we're loaded that library. And to fit the ordinal regression model using the polr function, the syntax is really easy. Just polr y tilde x1 plus x2 plus z. Data equal to data, method equal to logistic. Okay, we'll fit that. And then we can summarize the model. You can see it has coefficients, have the beta estimates, standard errors, the t-values, but unfortunately no p-values. Okay, so we have to calculate p-values by ourselves. And there are AIC value. That means the parameter estimation is the maximum likelihood estimate. And by using the AIC value, we can actually do model selection later on. Okay. All right, and if you want to calculate the odds ratios, you can just using this code, just exponentiate the regression coefficients. You can even put confidence intervals around them. Okay, so yeah, now it's a good practice to report odds ratios and their confidence intervals. Okay. All right, that's a quick introduction about fitting an ordinal regression model using R. But then we have some post hoc work to do. For example, the model we fit is called a proportional odds model. Okay, so there's a proportional odds assumption. I don't have time to cover the mathematics of this model assumption, but I will show you how to test it in R. Okay, so basically we need to load the library. We don't need to load mass again, but we need to load the library called the Brant. Okay, and we can fit the model again. And then we simply use the function Brant to perform the so-called the Brant test. Okay, so basically Brant test and print it out. You can see there's an omnibus. That's the overall test for the proportional odds, and for each predictor, you have a proportional odds test. Okay, so if we choose 0.05 as the cutoff value for making the decision for hypothesis testing, it seems the proportional odds assumption holds for all the variables and also for all variables as a whole. Okay. All right. And if you want to, say, check goodness of fit, there's a package called PSCL for McFadden's pseudo R square. So that gives you a little bit idea about the model fit. So the function is PR, lower letter P and capital letter R, PR2. Then put in the model object. And you can print out the R square here. It has several different statistics there. I think there's a LLH is a log likelihood, I think, and you have log LLH null. That's a log likelihood for the null model, and G2, and you look into the McFadden, that's the R square you are looking at. Okay. So for this model, it's like 3.2%, not very close to 1, right? So the model is not really good. Okay. Of course, you can perform likelihood ratio tests since we have maximum likelihood estimation here. So first, you need to fit a null model, which is y regressed on the intercept only. So the formula is y tiered 1. Okay, everything else is the same. And then you can perform the likelihood ratio test by using the function ANOVA. So ANOVA the null model, and the model, you just fit the full model, model polr, and you say test equal to chi-square. And you can print out that likelihood ratio test. So it shows the null model. The first row, the second row is x1 plus x2 plus z. That's the model we fit, and the p-value is very, very small. So that means the model we fit is significantly different or significantly better than the null model. So it's worthwhile to fit the model. Okay. So even though the pseudo R square is small, but it's still worthwhile. Okay. All right. Of course, so if we accept this model based on the likelihood ratio test, then again, the most important thing is we want to know if the effects are significant or not, right? So, and from the coefficient table in the summary outputs, we did not see a p-value for each effect. So basically, we need to calculate them by ourselves. So coefficient estimates, you can extract using the coef command. Unfortunately, you have to do a little bit more to get the variance. The standard errors, which is your square root of the variance, but you can see the syntax a little bit complicated here. But if you use the function VCOV, and then pick the diagonal element, square it, you get the standard errors, and you compute the z values, and you use this formula to calculate two-tailed t-test, and then you can perform a Wald test result. Okay, so you can print out the whole table, so get the beta estimate, standard errors, z values, and p values. Okay, and looks like they are all, yeah, and I think the ZB and ZC, because it's a categorical variable, so the ZC is the level C compared to level A. So that seems to have p-value of 0.15. So that's not significant. Or and all others seems to be less than 0.05. Okay, so all right. Of course, you can also use the likelihood ratio test to test the significance of one predictor or a group of predictors. Okay, because you can always fit the full model and then the model with the variable you want to test. Okay, so for example, if we want to test the significance of x1, so we can fit a reduced model using y tiered x2 plus z. So now x1 is not in the formula. So let's fit the model, and then we can perform likelihood ratio test using a ANOVA function, and then can print out the likelihood ratio statistic. And based on the p-value here, the p-value is rather small. That means x1 is a significant predictor to be added to the model. Okay, you do not need, and you do not drop it. All right. There are several other R functions you can use to fit ordinal regression model. They're more complicated. Some can even, you can add random effects to it, but I'll try to cover them in another video. So this is a plain vanilla approach for fitting the preferred odds model for regression model for ordinal responses. Thanks for watching.